Hi, this is a video series on linear algebra for business analytics. My name is Teja. The last video, we briefly discussed a system of, what does the system of linear equations mean and how are they related to matrices and linear transformations. We also saw how the notion of, the determinant concept that we introduced a couple of videos ago influences, whether the solution exists or maybe there are too many solutions and so on. Another way to capture this, to understand about solutions for systems of linear equations is through the notion of column space. Okay, what is a column space? As column space is nothing but the span of the columns of the linear transformation. So in this case, let's say we have this matrix A, which is the representation for the linear transformation. You know that the matrix A has some entries. For example, in 2-dimension, it will be A, B, and C, D, let's say. Then you can interpret each column as a vector, right? And if you have vectors, let's say V1 and V2, we discuss what is a span. A span is a set of all linear combinations of these two vectors. For example, 10 times V1 plus 5 times V2, or 1.1 times V1 minus 3 times V2, and so on. So there are many such vectors. So that is the column space. So that is the span, which is a collection of vectors. Okay, and these, a span is also called a span. I'm just introducing a new terminology that you might also come across. It's also called a subspace. Okay, I mean, so why is it called subspace? Remember, space was just the collection of vectors, right? For example, in 2 dimensions, it was a collection of all 2-dimensional vectors, or in 3 dimensions, the collection of all 3-dimensional vectors. So any numbers that you put in, for example, in the first coordinate, maybe A, B, and C, any of these numbers, put any numbers there, and then the collection of all such vectors was the span. Was the space of 3-dimensional vectors. Now, okay, so why did I introduce the notation of subspace? Because so this was the space of all vectors. A subspace would be a space of maybe all vectors, maybe some vectors. Okay, for example, remember that we had this idea that what if we were looking at the span of 1 0 0 and let's say something like 0 1 0. Okay, these two vectors are in 3 dimension, but the span is only can only capture a plane, right? I mean, in this case, it can only capture the 2D plane in 3 dimensions. So it will not, it will capture all vectors in this plane, but nothing outside the plane. So that means that this is called a subspace. So the span of these two vectors could be called a subspace. Span of any set of vectors is called a subspace, actually. And it's called a subspace because it's a smaller collection of vectors than the full space in 3 dimensions, right? A lot of other vectors are not a part of this space. Okay. And it's also, also why are we calling it a subspace is because any other vector, any linear combination operations that you do on that space give you a vector on that space only, right? So it's kind of nice in that way. Okay. So let's see. So let's say here we said we have a column space of A. So let's look at a 3-dimensional example. So let's say A is something like this, right? 0. So okay, 0 1 0 1 0 0 and maybe 1 1 0. Okay, so this is a 3-dimensional transformation. It's taking input vectors which are 3-dimensional and outputting vectors which are 3-dimensional, right? Now you can see that the span of A of the vectors of the columns in A, okay, they don't encompass the output space, which means the span is again restricted to a particular plane. In this example, it's just the 2-dimensional plane, maybe the xy plane here. then you know that the determinant is actually equal to 0, right? Because you saw in the last video that if you have a cube, what does linear transformation do for that? Maybe, I mean, in this case, it's actually squishing the linear transformation to be only on that xy plane and nothing on this side, on the z side. So this volume of this plane in 3 dimensions is 0. So that's why the determinant here is 0. So so that's what happens for some transformations. Some transformations don't encompass the columns of these transformations don't encompass the output space. So that is fine. So there could be transformations like that. So there's a way to capture that property that they don't encompass the output space by a simple number, which is called the rank. Okay. So rank of a transformation, so rank of a matrix or rank of a linear transformation is nothing but the this dimensionality of the span of the columns of A. Columns of A are the important ingredients here. They are, they characterize the linear transformation. The span of them is all the vectors that are possible using these columns and their dimension. For example, they can, in this case, they are only spanning 2 dimensions here. They cannot come out, right, in this example at the top. So this is called the rank of the linear transformation. Okay, it's nothing but the number of linearly independent vectors in vectors which are columns of A, in columns of A, when you interpret the columns of A as vectors. Okay. For example, if you think of this transformation, which is a transformation going from let's say 3 dimensions to 2 dimensions. So let's say this is transformation is AB, AB, and AB. What do you think this the rank of this matrix is? The rank of this matrix is the number of linearly independent columns. In this case, the number of linearly independent columns is just 1, because the first, second, and third column are just the same as the first column. So maybe if I had 2 here and maybe I had 3 here, it will still be rank 1. Okay. So that's just an example. So now for the last part, let's just I'm going to introduce another terminology called the null space. Null space of a linear transformation. Remember, column space of linear transformation, rank of a linear transformation, which is the rank of a matrix, null space of a linear transformation, or null space of a matrix. Okay, so let's say we have a system of equations. So we have a matrix. Let's say the linear transformation is represented again as capital letter A. Then let's say A times some vector is equal to 0 was the system of linear equations. And I can drop this arrows notation, but let's say this was the system of linear equations where I make the right-hand side zeros, right? Then what A is doing is mapping a vector to the 0 vector, right? So maybe there's only one vector which gets mapped to the 0 vector, right? Maybe there are many vectors. Maybe there's a, if you think of the input space, let's say maybe there's vector v1, maybe vector v2, which also both map to, which both get transformed to the 0 vector in the output space, right? It could happen. Or maybe there's only one vector which maps to the 0. Okay, so the collection of vectors, this collection of vectors again, right, that map to 0 because of the operation of this linear transformation A are called the is called the null space of A. Okay. Note that if it turns out that if the rank of A, which is the linear transformation, is actually the rank of A is equal to the number of columns of A, let's say, then there's only one vector, 0 vector, which gets mapped to, sorry, there's only one vector, not the 0 vector. then there is only if the rank of A is the number of columns of A, then the determinant of A is not 0, right? Then maybe there is a single vector V. There will be actually a single vector V, which may map to 0, which will map to 0. Sorry. It need not be this case. So, for example, let's say there were two vectors, v1 and v2, as I wrote there, which both map to 0. That means that a times v1 is equal to 0, and a times v2 also equal to 0. But remember, a is a linear transform. A times plus 3v2 also times a v1, which also evaluates to 0, right? So any vector in the span of these two vectors also evaluates to 0, which means that we actually have a subspace, and essentially a collection of much just v1 and v2. So it's the span of all of these two vectors, the span which includes all sorts of vectors, which also belong to the null space of A. Are two different vectors which belong to the null space of A, or which evaluate to 0. Okay, so that's it for this video. Thank you for watching.